Welcome to my presentation for the IEEE Sensor Conference in 2020. My name is Carolin Lohrberg and I'm from the Fraunhofer Institute for Ceramic Technologies and Systems from Dresden in Germany. I'm going to present you my paper with the title Development of a Mass Flow Sensor based on Low Temperature Cofired Ceramics for analysis of exhaust gas up to 500 degrees Celsius.
The results were achieved in a project called Amazing, funded by the Federal Ministry of Education and Research in Germany. First, I will give you a short introduction to the sensor principle for measuring exhaust gas. Then I'm going to present you the innovations and results for the low temperature cofired ceramic design and the low temperature transfer tape technology for high temperature stable packaging of the sensor. After that, I will show you my measurement results, and last but not least, I will give you a short summary and an outlook of our work. The state of the art of the sensors is that we have no mass flow measurement of exhaust gas possible due to high requirements, for example the high exhaust gas temperature. The exhaust gas mass flow rate is needed, for example, for the exhaust gas recirculation, the EGR. At the moment, the EGR rate is calculated via MOLAS, an indirect measurement of air pressure and temperature. A precise and direct measurement with a mass flow sensor could optimize the EGR rate, and that would improve the efficiency and minimize emissions. Such a sensor has to be high temperature stable, robust and pulsatile, which only ceramic materials can handle. A second field of application next to the EGR would be the measurement of real-time exhaust gas flow with portable emissions measurement systems, so-called PEMS. Let's have a look at the principle. The measurement is based on the thermal anemometry, which is very fast and sensitive. Besides, it is best known principle in industry for measuring fluid flows and has no mechanical tearing parts. The picture shows you a schematic of the principle adapted to detect pulsations. As you can see, there are two heaters in a row and two temperature sensors in a row. With two heaters in a row, you can measure forward and backward flow very fast, which is needed to detect pulsations. So for forward flow, heater 1 is cooled more than heater 2, and the other way around for the backward flow. The temperature sensors measure the gas temperature, and with this information the heater temperature is set. It is constant 100 Kelvin above the gas temperature. So when the gas velocity is high, the heater is more cooled, which results in a higher power consumption. This relates to the flow velocity. King described that first in 1914 and is now known as King's Law, which you can see on the right side. I will now present you the steps which are needed to develop and manufacture a mass flow sensor and ceramic multilayer technology. First of all, the material needs to be selected. After that, we have the design and the layout of the sensor. The two most interesting parts are the two innovative fabrication processes I'm going to show you today. First, the LTCC sensor itself. For a fast responding and sensitive sensor, there are some adaptations necessary. Secondly, the fabrication process of the LTTT packaging technology for electrical and mechanical bonding to a carrier. And at last, the measurement results. I'm going to start with the innovative fabrication process 1, where you have the requirements of detection of the gas pulsations. So we need a fast response. The challenge is here that we need a small thermal mass. So the substrate thinning and temperature sensors in heat area is necessary. So we have here three technologies we will have a look on. So the first one is the standard process technology with the use of ultra-thin sheets. So the thickness is here 50 microns, which results in 40 microns after sintering. The second process is laser ablation. Here we can gain a thickness of about 20 to 40 micron of the membrane. Disadvantage is that a precise parameter configuration is essential and it's a subtractive process. The last innovative process is an additive process in contrast to the laser ablation. This technology is established and we can gain here membrane thicknesses under 20 micron. You can see in the picture the ultra-thin membrane done by screen printing. So how does this multi-layer process look like? In the scheme, you can see the standard technology explained for the mass flow sensor with ultra-thin sheets. First step is tape casting a slurry, which is a mix of glass ceramic and organic binder, onto a carrier sheet. After drying, it is a flexible green sheet. It is cutted in different sizes. Normally, we prefer 4 to 4 inch. These tapes are then structured by punching and laser processes. The electrical circuits, in this case temperature sensors and heaters, are screen printed on the tapes. Wires are filled in mask printing to get the vertical electrical connections. The active metallization parts are passivated, again in a screen printing process. Next, all layers are stacked and laminated together. While sintering in an oven, the organic burns away and the glass ceramic gets densified. An optional laser process reopens the cutout. At last, the ceramic wafer is diced to separate all sensors. Let's compare the standard process to the additive process done by screen printing. In that case, a sacrificial layer is necessary to carry the membrane. You can see the important steps for both fabrication processes in a cross-section scheme. Left, you can see the standard process with ultra-thin tape, and on the right the LTCC process with printing technology. The membrane is screen printed onto the carrier, the sacrificial layer based on carbon. And after that, the metallization and the passivation can be printed onto the membrane via screen printing. Stacking and laminating follows, and the fabrication process finishes with sintering process. The sintering process is adapted so that the sacrificial layer has time to burn out. So on this slide I want to compare the results of the innovative fabrication process 1 with the standard technology. We prepared sensors with different membrane thicknesses. One has a 100 micron thick membrane prepared with standard LTCC process, analog to the standard process with the ultra-thin LTCC sheets, which results in a 14 micron membrane. The new technology with screen printing, the membrane, instead of using LTCC green sheets, results in a 20 micron membrane. You can see all three kinds of sensors in the picture below. They differentiate between each other in their translucency. Right is a SEM picture of a printed membrane with integrated active parts based on platinum. Now I will go to the next innovative point, the LTTT packaging process. LTTT stands for Low Temperature Transfer Tape. First of all, we need to check on our requirements. We need mechanical and electrical joining of the sensor to the aluminum carrier. As well, the temperature stability should be minimum 600 degrees. Better would be above the 600. The classic joining differentiates between electrical and mechanical connections. Normally, for electrical joints, wire bonding is used, and the mechanical stability is aimed with adhesives, soldering or glass soldering. Only glass soldering comply with our requirements. Joining with sintering fulfill both electrical and mechanical joint at the same time. And the temperature range is much higher compared to the standard technologies. So the 3D scheme at the right shows the setup. We have the LTCC sensor, the LTTT tape, and the alumina carrier. The LTTT has wires and cutouts and can be handled like normal LTCC green sheet. They are stacked and laminated together and then sintered, where the joining of the electrical and mechanical is made. The challenge in the LTTT process is finding the optimal sintering parameters. We started with the standard sintering process you can see on the left. Here we had an insufficient bonding, electrical and mechanical, as you can see in the cross-section. The other sintering technology uses a defined pressure while the sintering, the so-called pressure-assisted sintering, you can see on the right. First of all, we had to investigate the optimal bonding pressures. In the pressure range of 1 MPa, an electrical connection is there, but as you can see in the cross-section, the mechanical joint is weak. In the pressure range of 10 MPa, we had found the optimal parameters. We have a good electrical and mechanical connection. You can see on the right. But if the pressure range is too high, cracks and bulges occur in the sensitive membrane, which is shown at the picture down left. So we could establish a functional joining technology which combines electrical and mechanical joint in one step and for high temperatures. So after finding the optimal process parameters, it is possible to measure the sensors. We started with a resistance over the temperature curve with the different membrane thicknesses up to 500 degrees. Here you can see the results compared to the PT1000 curve. So 20 micron membrane thicknesses and 100 micron show an excellent fit to the curve. On the other hand, 14 micron membranes has a much higher drift. The reason can only be found in the different fabrication process, since all materials are the same in all processes. And as you can see in the diagram, the printed membrane shows very good results. So the second measurement was the first initial mass flow measurement in exhaust gas. The sensor was integrated in low pressure EGR behind the cooler. The gas temperature was about 100 degrees Celsius. The red curve in the diagram is the reference, which calculates the mass flow with the information of temperature, pressure sensors, and the air mass flow sensors. We tested the different membrane thicknesses. Here you can see the results for the 20 micron membrane sensor, which is the black curve. The sensors show every change of the gas mass flow very precisely. It is seen how the black curve follows the red one. Slightly differences are seen in the absolute mass flow value. The first step at about 46 kg per hour, the black curve is drifting away. The smaller steps show no drifting and have stable values, but different to the reference one. That could be a calibration error. The drifting in the first step has to be analyzed furthermore, if the sensor is drifting for real or the mass flow decreases in real. So now I will finish my presentation with a conclusion and an outlook. I could show you a ceramic-based mass flow sensor for measuring exhaust gas, a new fabrication technology for ultra-thin ceramic-based membranes, and a new fabrication technology for joining LTCC and alumina with temperature stability up to 800 degrees Celsius possible. I presented you that we can measure mass flow with this innovative sensor up to gas temperatures of 500 degrees Celsius. We tested it as well up to 600 degrees Celsius in an initial test. The development of sensors for higher gas temperatures is ongoing. Our first measurements results showed good coefficients, and we could prove the functionality in initial measurements in exhaust gas. In future measurements with higher gas temperatures are planned, and as well the proof of pulsation capability with model simulations and in tests.
Thank you for watching my presentation. I hope it was interesting for you. Feel free to ask, and thank you and goodbye.